David Stringer. Welcome to R-2000, the Better Built House. In the last few programs, we've been looking at mechanical ventilation systems. We've seen the need for ventilation and looked at some of the factors that influence the design and installation of effective ventilation equipment. In this program, we're going to look at one option of reducing the costs of providing that ventilation with heat recovery ventilators. Only we're not going to start with this heat recovery ventilator. Yesterday, Oliver stole the TV crew and went to a research lab where they're testing this kind of equipment. Let's see what he got.
I'm here today at the Ontario Research Foundation. It's in this building that scientists validate the performance of the units that I install in the field. What they're looking for is the efficiency of various units and the amount of airflow that those units deliver in air-to-air heat exchangers or heat recovery ventilators. We're going to be getting into that a little later on. But I don't want to disappoint David, and I know that at this time in the program we usually have a review, so here it is.
Ventilation is an important requirement of the Better Built House. A mechanical ventilation system must be properly sized to meet the fresh air requirements of the house and must be designed to provide fresh outside air to each room of the house. The ventilation system must be capable of exhausting stale air, household pollutants, and humidity from those areas in the house where they are produced. Finally, the ventilation system must be designed to supply the fresh air to the homeowners in a comfortable manner.
Last show, we looked at a couple of different options for preheating incoming cold ventilation air. One of those options was to use a plenum heater. Another was to mix that air with house air before it was delivered into the living space of the building. That's an extremely critical issue in colder climates. However, both of those options can tend toward being expensive. And today, we're going to look at a different way of going about the whole thing.
The exhaust air stream of the ventilation system will carry as much as 200 CFM, cubic feet per minute, of heated house air. By recovering some or all of the heat being exhausted, significant energy savings will be realized. The heat recovered from the exhaust air stream can be used to preheat the incoming air or to contribute to the hot water requirements of the building.
What we're going to be looking at is an option for recovering heat from outgoing exhaust air and using it to preheat ventilation air. And luckily, we've been able to second Colin McGugan from the ORF for a day so that he'll be able to show us around and tell us how this stuff works. Hi, Colin.
Good morning, Oliver.
Really appreciate your taking some time out to do this with us. I'm going to start with a dumb question because I've been taught everything I know by my host, David Stringer. How does an HRV work?
Well, the primary function of the HRV is to provide ventilation air for the house, but it also recovers heat from the outgoing exhaust air for use in preheating the incoming supply air. What happens is we have an HRV set up here for a demonstration. The cold outdoor air comes in through the heat exchanger on this end. The warm exhaust air comes out through there. As they pass in the core, the heat is transferred from the exhaust air to the supply air. This is important in that it helps to warm the supply air so you can eliminate problems that you would have with bringing in cold, fresh air into the house.
Well, it's a very convenient package in that sense, and I know that's why I like them as a builder, because I just have a prepackaged unit that I know you've tested, which I can just stick into my buildings. But rumor has it that there have been some problems with these machines. What's being done to resolve those problems, Colin?
Well, for one thing, we've developed a standardized test procedure so we can rate the performance here in the lab. This has already resulted in a substantial improvement to the performance of the units that we've seen coming out on the market. Also, the installers have developed a standard training course for their people, for the industry, so that they can do a better job on installing the units. So what we're seeing is a better designed, better installed package getting out in the field.
Well, I guess the next question I want to ask is just exactly how do you go about testing these things?
Okay, Oliver, before we go down to the lab, I'd like to show you some of the components of the HRVs. We've got a few units taken apart here so you can see what's inside them.
I'm looking forward to this.
Okay. First thing we have on the end here is the fans. The unit does two things. It basically takes air from the house, exhausts it out through this fan to the outdoors. It also pulls in fresh air from the outside through the heat exchanger and dumps it into the house. It's very important that these fans are sized to move the same amount of air.
Balanced system.
That's right. So it's also important that they be able to meet the minimum ventilation requirements of the house.
Mm-hmm.
Another thing we look at on these is the power consumption of the fan motors. Since they're running all the time, it's very important to see how much energy they are using.
Understood.
The next thing we look at in the units is the heat exchanger cores, which we have here. What happens is the warm exhaust air from the house comes out through the unit, out through these cores into the outside. The cold, fresh air is brought in through the cores and dumped into the house. As the two air streams pass by each other in the cores, the heat is transferred from the warm exhaust air to the cold supply air so that it's preheated when it comes into the house. This type of core is plate type, which is quite common. We also have the heat pipe type core, which is another one of the common ones. A couple of the important aspects of heat transfer in the cores is the surface area of the core. The greater the surface area, the better the heat transfer, and the temperature difference in the core. The higher the temperature difference, the greater the heat transfer.
And presumably one of the problems that can occur here is the fact that as the outgoing humid air from the building is chilled, one can get a condensate, and that condensate is dropped into this drain, this plate, and then drained away.
It's very important that the installer make sure that this drain is connected up for the units.
Okay. Is there anything else that a builder should be aware of?
Yes, the controls on the units are very important. Here we've got a unit where you can see the controls shown on the end panel here. What we have on top is a connection for a remote switch where the homeowner can have it located in his bathroom or kitchen. You can use this switch to turn the unit on from low continuous speed onto high speed for extra ventilation whenever it's needed. We also have a manual on-off switch located on the unit so it can be turned on to high or low speed as required. And at the bottom here we have an automatic dehumidistat which will turn the unit on to high speed whenever the humidity in the house goes above the set point on the stat.
And presumably the only other control that's of concern here is the defrost mechanism that's being employed.
That's right. There's a couple of different ways of doing the defrost. The first one on this unit is what we call a fan shutoff, where the cold outdoor air is actually stopped from coming in through the unit and the exhaust air is left running. What this does is heat up the core and allow any frost or ice to melt off and drain away. On this type of unit behind us, we have an electric preheat coil. Back in behind this plate here is an electric heater which heats up the air. What it does is make sure that the outdoor air coming in is heated up so that when it hits the core, it doesn't cause any frosting.
And presumably you also have to look at the energy requirements for these preheaters as well when selecting a unit.
That's right. If you have a lot of cold weather, these can use a substantial amount of energy.
Okay, let's see if I'm capable of summarizing this. The first issue is the size of fans to ensure that the system is balanced, and that obviously affects the performance of the unit. The second thing is that we have to make sure that we understand how large the core is and what configuration it has, and that affects the performance of the unit. The third item would be the temperature difference, and the fourth item is the defrost strategy. How'd I do?
Pretty good.
Let's go see how they're tested.
Okay.
This is an engineer's paradise column.
This is where we do all the actual testing on the units.
So the unit that we passed just there on the floor is actually being tested at the moment.
That's right. That's connected up to all our instrumentation. We've got a schematic here showing all the instrumentation that's hooked up to it. It's all fed from there into our computer here where we process the data from the tests.
How long does it take to test a unit?
It takes about 2 weeks to run through the full series of tests.
And what are you testing them for?
We test the airflow and the efficiency of the units at 0 degrees C and at -25. We also look at the defrost characteristics of the unit at -25, see whether it plugs up with frost and how it's operating.
It's pretty thorough. How many units have you tested?
We've tested about 25 so far.
And is there any information available to builders regarding the tests?
Yes, all the information from the testing is summarized on this specification sheet. This is prepared for the R-2000 program and published by them.
And it's available also through the manufacturers, I suppose?
Yes, they distribute it out to the manufacturers and through their local offices.
Well, you know, Stringer is always trying to get me to tell him what the best way to build a house is. Since I've got you here, I'm tempted to ask you the same question. What's the best HRV?
I can't really tell you that, but I can tell you the types of things you should look for when selecting a unit. Obviously, heat recovery efficiency is one of the things you should be looking at. The units we've tested typically range between about 50 and 70% heat recovery efficiency. Obviously, for most units, this drops as the outside temperature drops. There's also other things you should be looking at besides the heat recovery efficiency. The unit must be capable of meeting the minimum ventilation requirements for the house. It also must be installed properly so it operates quietly and efficiently, and the homeowner must be able to control the unit to get the best operation out of it.
Well, I can certainly relate to the concerns regarding installation because I have those concerns myself, and I'm going to be going out into the field and looking at a number of installations. I really want to thank you for taking the time to show us how you go about these tests.
Oh, you're very welcome.
Thank you very much.
Well, I haven't seen you for a while. Did you have a good time at the ORF?
Yeah, it was very interesting. They're testing a whole bunch of these units, and they've really got a very, very scientific approach to what they're doing. The key issue, however, is the way in which these units are installed.
Right, you don't want to spend a whole bunch of money and then have it ineffective because of the installation.
Exactly.
This is kind of a tight installation.
Yeah, it is. This is an unusual installation because it's in an attic. We are not in the basement of this building because it doesn't have a basement.
I guess, though, it points out that the HRV doesn't necessarily have to be in the basement.
No, that's very true, but it has to be in a heated space.
Mm-hmm. But other facets of this installation are common, right? Like the rubber straps, the flexible ducting.
You've been doing some homework. Yeah, they're fairly common. The point here is that you've got to have rubber straps in order to isolate this unit for vibration against the frame, and you also want to insulate the ductwork to cut down any of the vibration that's in the duct itself.
Right.
How did you learn all this stuff?
Oh, well, while you were gone, I was busy being nosy, thumbing through the installer's manual for heat recovery ventilators. Mm-hmm. It's quite a document, and full of all sorts of useful things, like remembering to locate the unit near an electrical outlet. I would have forgotten that. And to make provision for the condensate drain, which I'm glad they remembered here in the attic.
I'm sure the builder's glad as well. The point about this particular course is that individuals installing these units can only do so in R-2000 houses if they've taken the course, and that's pretty well the same theme for all the other trades in the entire industry. One of the things about these houses is that we're looking for the very best performance from all our tradespeople.
And it's interesting how many simple, logical considerations there are for the installation of one of these.
I agree. Let's take a look at the ducting that's required to put one of these units in and some of the considerations regarding that. We know that this thing has to be in a centralized location. What does the book say about that?
Oh, you want me to do this? Okay. That kind of centers around the ductwork that goes from this unit to the outside because it's an insulated, flexible ducting. Mm-hmm. It's insulated because the air in those ducts is cold and you don't want the humidity in this room to condense on the outside of those pipes and be a problem. But as I understand it, this stuff kind of restricts airflow a little bit, and it's also expensive. So you locate the unit centrally, but near an outside wall to minimize the runs of that.
Right. The name of the game is the best airflow, the best installation we can get for the least amount of money.
Okay. Now, as far as the exhausts from the house go, you want to pick up the air in places where pollutants are created, like the bathroom, the kitchen, and the book even suggests the basement workshop. Mm-hmm. As far as the fresh air intake from outside, it's got to be in a place where it actually picks up fresh air, like not right where the tailpipe of the car is when you run it for 5 minutes in the morning.
A really important point. In fact, the exhaust fumes from the car are very dangerous. You also have gas meters, you have oil filler pipes, and of course the thing has to be located away from any area where you might have garbage, and you don't want it covered by snow either.
Mm-hmm. Now, and when you bring that fresh air in, it's still a tad cooler than the house air, so the vent should be located high in places where that air is going to mix with the house air thoroughly before it hits the people.
I think we're starting to become a pretty good team here. You want to go on the speaking circuit?
I don't think I could keep up with you for a minute, but I am learning things. I learned today that by using a heat recovery ventilator, money can be saved on the fuel bills at the same time that it's providing that air comfort and quality. But kind of most interesting to me was that the very installation alone is a key component of the better built house. Next week, we're going to continue looking at mechanical systems in R-2000 homes. We're going to look at heating systems. Join us.